I hate to sound unfair, but look, it's the truth. All routing protocols are not considered equal. In this CBT Nugget, we'll go ahead and delve deep into this statement, and we'll take a look at some great concepts that are going to assist you when it comes time to designing the Layer 3 routing protocol used by an organization. So what we'll do in this particular nugget is we'll go ahead and first talk about some routing concepts, some fundamentals to dynamic routing. This will be a review for most of us. Then we'll go ahead and we'll talk about the characteristics of specific routing protocols that we can choose, and then we'll wrap it all up by literally taking a look at some of the most important deployment design characteristics when it comes to a layer 3 routing protocol infrastructure. Now, you probably shouldn't really talk about the fundamentals of designing routing protocols without revisiting distance vector. Yeah, that first generation of technology. With distance vector, we have our routing nodes exchanging with each other the complete full routing table. That's right. And they do this periodically. What is it with RIP? Every 30 seconds, right? Every 30 seconds, RIP is going to go ahead and send the full complete routing table to its neighboring devices. Now, sure, RIP version 2 does this in a multicast concept instead of a broadcast, but still, the entire routing table sent to neighboring devices every 30 seconds. What's the problem with this distance vector approach? Well, if the network is converged, you're doing all of this communications about prefixes completely unnecessarily. Yeah, I mean, why send everything you know about the routing table every 30 seconds if nothing's changing? Here's another thing that we just really get annoyed with when it comes to RIP, and that is it's routing by rumor. Okay? Look at it this way. Device 1 has this routing table, and it passes it to device 2. And it combines it with its information, and then it passes it to device 3, and now device 3 has this information. If there are any errors introduced by either of these devices, R3 takes those errors and considers them factual information about the network. This actually reminds me of a game that we played way back when I was in elementary school. All of us students all sat in a big circle, and the teacher walked up to the first student and whispered a phrase in that student's ear, and then that student would whisper that phrase in the next student's ear, and so on. It was amazing. Once that communication got all the way back around the room, the original phrase that was whispered in the ear of the first student did not resemble the original phrase in any way. I mean, the phrase was completely distorted. If the teacher had spoken, the sky is cloudy with some sun, by the time that phrase made itself all the way around the circle, it had been distorted to next Tuesday there will not be any homework. I mean, it was absolutely remarkable how distorted the information became. Well, here I am decades later, and this reminds me of distance vector routing by rumor, where the routing table is moved from each device, and sure enough, this could lead to the propagation of incorrect routing information. So, of course, distance vector routing protocols gave way to link state routing protocols. And with link state routing protocols, we don't have routing by rumor. What we have is we have the routing nodes taking things that they have direct awareness of, like their link states, and sending this information to the other devices in an area. That's right. Notice this is these devices sending information about stuff they definitely know. And then these receiving devices will take this information, they will put it in a topology database, and they will derive their own map of what the network infrastructure looks like. Notice they are not relying on a table of what the network looks like. They are deriving their own depiction of paths through the network through the link state information that they receive. We said RIP was a great example of a distance vector routing protocol. Well, OSPF is a great example of a link state routing protocol. Now, it is worth mentioning Cisco had to go and get really, really super creative on us, right? Yeah, Cisco had to go and get really creative on us, and they had to create a new category called hybrid. And a hybrid routing protocol, there's only one of them, and that is EIGRP. EIGRP, as of February 2013, is now an open standard. Cisco has released EIGRP into the wild, so we will see it be an open standard. Up until February of 2013, it was a Cisco proprietary protocol. And sure enough, what they did with this was they looked at distance vector and they said, let's borrow what's good from that. They looked at link state routing protocols and they said, let's borrow what's good from those. And they tried to build both of those features into EIGRP. Now, one of the other categorizations that I need to remind you about is the fact that with routing protocols, we're going to divide them between interior gateway, we call them, and exterior gateway. Now, here's the great news. There is only one exterior gateway protocol. So, here is ABC Company. Boy, is that overused or what? And then here is XYZ Company. You don't hear about that one as much. Okay, and the routing protocol that would be used to share prefixes between these organizations, this is called an exterior gateway protocol, and as you know, there is only one, BGP. The reason why there has been only one for so long is something actually called MP-BGP. These are multi-protocol extensions that can easily be added to Border Gateway Protocol. For example, we have talked in this CBT Nugget series about IPv6. You need BGP to be able to carry IPv6 prefixes? No problem. Don't create a new version of BGP. Just add these particular prefixes to what BGP can carry through these multi-protocol extensions. Pretty cool. Now, what about interior gateway protocols, IGPs? Well, here we have a bunch that are in use today. You have RIP v1. This would be for very, very old equipment in a very small routing domain. RIP v2 would be more common in your small domains these days. We have EIGRP. We have OSPF. We have ISIS. Intermediate system to intermediate system is a competitor to OSPF, and where you find that used as an IGP is in big internet service providers. Yeah, a lot of big internet service providers went for ISIS because it is more flexible in its design than OSPF, and they went and stuck with it. You won't find ISIS outside of many ISP type of environments. Sure, there's definitely some companies out there that are being really bold and unique, and they're running ISIS as their IGP. But as I said, most of those you would find would be internet service providers. So there's a look at the landscape when it comes to routing protocols, and we know one exterior BGP and a whole choice of interior gateway protocols. You might say, hey, Anthony, whatever happened to IGRP? And IGRP was the predecessor by Cisco to EIGRP, and it is absolutely legacy. And what I mean by that is Cisco routers manufactured and sold today don't even bother to include it. So I left IGRP off our list for good reason. Now, when you're thinking about choosing a particular routing protocol for an organization, one of the big things that's going to come up is convergence. That's right. Convergence speaks to when there is a change in the network infrastructure, how quickly will all of the devices be educated about that particular change? Think about a RIP environment. With a RIP environment, we have 3 nodes here, and there's some kind of change out here, and there'll be a 30-second update that gets sent to device 2. After 30 seconds, device 2 will update device 3. And sure enough, now we have convergence. This potential 60 seconds of time that has elapsed is considered outrageous in today's terms. We want things in milliseconds. We want convergence to take place in milliseconds. We would never want to wait multiple whole seconds in order to learn about some change in the network infrastructure. Now, in all fairness to RIP, I just told a very simplified version of RIP's story. You see, one of the things they invented for RIP was something called triggered updates. And sure enough, with triggered updates, if there's some change out here, RIP can fire almost immediately an update, and then R2 would get that update, and it would fire a triggered update. So they did indeed engineer new features into RIP to try and speed convergence. But look, you're never going to have the speed of convergence with RIP that you would have with more sophisticated protocols. Let me give you an example of what EIGRP can do. EIGRP, let's say, here's one of the things it can do. So let's say this is router 4 running EIGRP, and then over here we have router number 5, router number 6, and then over here router number 7. Notice there are 2 paths to get from 4 to 7. And what router 4 with an EIGRP environment can do is it can have the path through, let's say, 5 in its routing table. And then in its topology table, it can have the alternate path through 6. Now what happens is, let's say router 5 crashes. So now router 4 knows it has to go through router 6. It immediately, in a fraction of a second, installs the new route into the routing table from the topology table and starts moving traffic successfully through the alternate path. By the way, you might know this term. This is called the feasible successor. This backup path in the topology table that can immediately be installed in the routing table as the successor route. So the feasible successor immediately becomes the successor. So here we have a failure of a router, and within milliseconds, we have this router passing traffic through the surviving path. Nothing like this exists in RIP. I mean, we're not even close in a RIP world to mechanisms like we find in more advanced routing protocols such as EIGRP. Now, we just left off there talking about EIGRP, so now would be a great time to walk you through some more characteristics of EIGRP. Remember that feasible successor thing I just mentioned? Well, that's all part of the diffusing update algorithm. Yeah, we know that OSPF uses the shortest path first algorithm in order to choose best paths. Cisco invented something called dual for EIGRP to use, and it consists of that successor, feasible successor type of logic that we reviewed a moment ago. With EIGRP, it is very, very fast to converge. So on any brochure for this protocol, you would see fast convergence highlighted. Of course, we can do variable length subnet masking with EIGRP. This is because EIGRP is what we call classless. Remember, a classless routing protocol will send subnet mask information in updates. This is considered good form, and it allows us to variable length subnet mask when we design the IP addressing infrastructure. EIGRP does something else that's really cool, and that is it's got a built-in bandwidth protection feature. Yeah, EIGRP is only permitted to use by default 50% of the bandwidth on a particular circuit. Pretty awesome. Here's something else. EIGRP has the ability to unequal cost load balance. Yeah, that is a very unique capability right there of this protocol. So you could have two paths to get to a destination. And this could be a T1 and this could be a T3. And you could say, you know what, EIGRP, go ahead and just consider them equal. And I want you to load balance across both of those links. So, very, very unique protocol, originally engineered by Cisco Systems, and it has some of the most remarkable features for a particular routing protocol. By the way, I'll add this to this description. It really is easy to configure. There is not much to the configuration of EIGRP, and that's why a lot of organizations love it in addition to this vast feature set. Now, we mentioned it earlier. We love to point out that it is a classic link state routing protocol. It's OSPF. OSPF is EIGRP is considered very simple to configure. OSPF would be definitely considered a bit more complex to configure. Remember, one of the things that we do to optimize OSPF is we run it in a hierarchical area type structure. You have a backbone area, and then you have areas that you can attach to that backbone area in order to have a hierarchy in your routing infrastructure. It will offer great convergence if you configure it correctly, and sure enough, it supports variable length subnet masking. Something else about OSPF is that it is going to be extremely tunable. Now, what do I mean by tunable? Well, it means that you can go in and you can create special area types like stub areas and totally stub areas and not so stubby areas. And these areas will do things like dynamic filtering of updates and automatic default route generations for you to reduce the complexity and the overhead on the devices in certain areas. I would definitely say that of all of our interior gateway protocols, OSPF is by far the most complex. We could do a full 25 nugget series here at CBT Nuggets just on OSPF. Sure, that would be very easy to do. It is that sophisticated and that complex. Now, BGP is our exterior gateway protocol choice. Pretty easy to choose which EGP you're going to implement for an organization. There's only one, it's BGP. And one of the questions I get all the time from students is, Anthony, is border gateway protocol distance vector or is it link state? I mean, what's going on with this particular protocol from a technology standpoint? And I always say, well, Mr. or Mrs. Student, it's neither. We really consider it a path vector protocol. You see, how they engineered this thing, let me draw in some autonomous systems here, because this is what Border Gateway Protocol is all about. It takes companies, which are equated to autonomous systems, I'll just draw in 3 here, and it exchanges prefixes between these autonomous systems. With IGPs, they function on a router hop by router hop basis. But with Border Gateway Protocol, we function on an AS to AS basis. Yeah, we don't care as much about individual router hops. It's how a prefix moves from autonomous system to autonomous system. Now, if this is Cisco, and this is a huge internet service provider like Verizon, and this is another big company like Microsoft, these companies want to have very fine controls over how their prefixes are shared. And they want to have fine controls over which exit their particular traffic will take. Cisco wants some traffic going this way. It wants other traffic going this way, maybe to one of its partner organizations. In order to have all of these fine controls, we need a whole bunch of different metrics that we can use to potentially manipulate the path that is taken. So, when it comes to Border Gateway Protocol and choosing best paths, we have values like weight that can be used, local preference that can be used, the multi-exit discriminator that can be used. Yeah, so many different values. There's even one called the AS path, by the way, which is basically just a hop count like you would have in RIP. It's just counting up the AS hops that you've taken to get to a destination. So, very sophisticated set of metrics that are used in this path vector exterior gateway protocol. Now, I'd like to wrap up our review of Border Gateway Protocol by telling you something that might be a bit of a surprise for you. Border Gateway Protocol features relatively slow convergence compared to our interior gateway protocols, and this is on purpose. Think about it. With this protocol being the protocol that is used to make the internet function, if you were to have a protocol that converged hugely rapidly, right? Very, very quickly, well, you would have complete chaos with the routing protocol in an internet perspective, wouldn't you? Yeah, things are changing dramatically all the time with internet prefixes. So with Border Gateway Protocol, we end up having slower convergence so we can have increased stability in the protocol. We sacrifice convergence for more stability with Border Gateway Protocol. Now, I'm sure you're happy to note that I really haven't done many asides as we've gone through our CCDA CBT Nugget series. But I must do one here. I had the privilege of being in a design engagement and then stuck around to teach individuals how to do the implementation at a massive, globally significant bank. Yeah, and this financial institution did something that was pretty remarkable. They took their existing and poorly designed OSPF infrastructure and they replaced this interior gateway protocol with none other than BGP. That's right. So in their autonomous system, they had BGP running as their IGP, and then they did BGP for traditional BGP purposes to other autonomous systems that, of course, run more traditional IGPs inside of them. Border Gateway Protocol became this company's IGP, and it worked terrifically well, and it solved a bunch of problems they were experiencing with OSPF as their IGP. Keep in mind what I said, though, in this particular example. The company was massive. Their interior structure was so complicated and so vast and so complex that it necessitated the huge scalability features of Border Gateway Protocol. But just something that I wanted to make you aware of that could happen out there with very large entities. Now, let's talk redistribution, shall we? You've gotten a great sense now for how you're going to choose the right routing protocol for the right job for one of the clients that you're doing a design for. I mean, great example would be they need a sophisticated routing protocol with very fast convergence. You're going to choose between EIGRP and OSPF depending on their expertise and what type of equipment they have. If they're an all Cisco shop, you'd definitely consider EIGRP while we're waiting for that to become much more accepted and on many more devices now that it just became an open standard. But here's the thing. What gets a little trickier is designing more complex environments that are going to run multiple routing protocols. Let's take a look at this. Let's say we have a core area of our network that is EIGRP. Okay, so EIGRP is the routing protocol in this area of the network. But then we have another area of the network infrastructure that is indeed OSPF. Okay, well, we can coexist these two routing protocols. What we can do is we can do two-way redistribution or bidirectional redistribution. We'll take EIGRP prefixes and we'll redistribute them into OSPF. We'll take OSPF prefixes and we'll redistribute them into EIGRP. Now, everyone in the OSPF domain has absolutely no problem communicating with prefixes in the EIGRP domain and vice versa. Now, students will look at this illustration and they will go, Anthony, now wait a minute. Isn't there a chance for routing loops here? Isn't there a chance where like packets and or even routing updates could circulate endlessly in the topology? And the answer is no. No, there isn't. You see, EIGRP has built-in safeguards and so does OSPF in this situation. Particularly, they both recognize updates as being external to their domain, and they punish those external prefixes with something that we call administrative distance. So, great news. There are protections in place against routing loop and routing feedback problems in this illustration. Where I need you to be careful is when you introduce another routing protocol into the equation. Maybe in this area of our network, we have the dreaded RIP. Now, your designers go in and they say, okay, well, we need full reachability, so we better go ahead and put the OSPF routes into RIP. We better put the RIP routes into OSPF. We need to put the EIGRP routes into RIP. We need to put the RIP routes into EIGRP. Now, when you add that third protocol and you're doing your two-way redistribution, now we can start to get into big problems. Yeah, we can really start to get into big problems here. You see, what'll happen is RIP as an example, starts getting very confused about how it should get to particular prefixes. It says, all right, well, I'm real close to these OSPF prefixes right here, so I'm going to send traffic into OSPF that way. But then it says, well, wait a minute, I just heard about those prefixes as being available through EIGRP. So I want to go that way to get to those prefixes. And then it hears the updates from RIP and it says, oh, no, wait, from OSPF rather. And it says, no, this is the right way to go. And then a moment later it goes, no, this must be the right way to go. So this is where things get messy. And how we handle this in redistribution is we do filtering. Yeah, when you start getting really, really complicated like this, you put in filters so that, let's say, these particular OSPF prefixes will not be reintroduced to RIP coming from this direction up here with EIGRP. Yeah, so we combine filtering techniques with the redistribution techniques. Now, I know what you're thinking looking at this mess that I've drawn. You're thinking, Anthony, just do yourself a favor and convert this whole mess to the protocol of choice like OSPF. And I got to tell you, that is the ultimate answer. We do not suggest multiple routing protocols to organizations. No way. But I bring up the redistribution design just in case for some short period of time you are stuck having to do redistribution with multiple protocols in your environment. So, my dear friends, in this CBT Nugget, we examined some review information, some fundamentals about routing protocols. We looked at things like distance vector versus link state and interior versus exterior. We talked about the characteristics of some of the most popular routing protocols in use today, and we gave some guidance on designing routing protocols, particularly the case where we're stuck with not just one, not just two, but maybe even three routing protocols that we need to have coexist with each other. Well, I hope this has been informative for you, and I'd like to thank you for viewing.